we have calculated and discussed the density of states of phonons, and we have also discussed the average energy of a mode, and we are now ready to combine the two to get the specific heat through the route of calculating total energy of a system where these phonons are there or a crystal with vibration, both are equivalent. So, let us see what we did. We said if I have an optical mode in this, take density of states to be independent of omega, and that means the vibrations are all at the same frequency. And this, we call this the Einstein model. And we also had Debye model, in which case we assumed that omega as a function of k is always equal to V sound times k, that is a linear dispersion, and in that case the density of states d omega came out to be V over 2 pi square omega square over V s cubed. So, this changes with the frequency, and then we had also calculated energy of a mode with frequency omega. This I will call average energy of a mode with frequency omega at temperature T, and this came out to be, let us call it E average, came out to be h cross omega over e raised to h cross omega over k Boltzmann T minus 1, and on the side it also meant that the number of phonons is equal to 1 over e raised to h cross omega over k b T minus 1. Number of phonons times the energy of each phonon h cross omega gives you the average energy. So, we will now combine all this and get the specific heat. So, let us first do Einstein's model. And this is applicable to optical phonons in a good way, because optical phonons have a very flat omega k versus k curve. So, in this case the density of states is equal to n delta omega minus omega 0, where omega 0 is the frequency of oscillation, and where n is the number of atoms or number of cells over which the boundary condition is applied. This is for one particular mode. This is an optical mode we are talking about. So, this is about one particular mode. It could be a transverse mode or a longitudinal mode. Total number of modes is going to be 3n. So, in this case when I calculate the total energy is going to be equal to integration over all omegas average energy of this mode times d omega. This is 0 to infinity, and this comes out to be, so let us write this again, E omega will come out to be 0 to infinity d omega h cross omega over e raised to h cross omega over k b t minus 1. D omega now is n times delta omega minus omega 0. So, this comes out to be h cross omega 0 over e raised to h cross omega 0 over k b t minus 1 times n. Now, for counting all modes, because remember this is one mode over which I applied the periodic boundary condition. There are two other modes. So, there are going to be two transverse and one longitudinal mode. I have to multiply this number by 3. You can think of it another way. These n cells, if there are n atoms or n units, all of them together are going to have 3n degrees of freedom, and we have calculated this energy only for 1 degree of freedom. So, actual energy is going to be E equal to 3n h cross omega 0 over e raised to h cross omega 0 over k b t minus 1. So, if all atoms vibrate with the same frequency, the total energy E comes out to be n times 3 h cross omega 0, where omega 0 is the frequency of vibration e raised to h cross omega 0 over k b t minus 1. Now, this is a little complicated expression. Let us learn about it more by taking different limits. So, if I take t going to infinity very large, then e raised to h cross omega 0 over k b t minus 1 is approximately equal to h cross omega 0 over k b t, and therefore, total energy E is going to be 3n h cross omega 0 over h cross omega 0 over k b t, and this term cancels and I get total energy to be 3n k b t, and therefore, C V, which is d E dt at constant volume because then the frequency would remain the same, is 3n k b, which is 3 R per unit mole, which is the Dulong-Petit law. Experimentally, you observe that at high temperatures the specific heat is 3 R or 24 joules per mole. So, I have E equals 3n h cross omega 0 over e raised to h cross omega 0 over k b t minus 1. As t goes to 0, e raised to h cross omega 0 over k b t goes to infinity. It becomes very large. So, I can neglect that 1 and write the total energy E as 3n h cross omega 0 e raised to minus h cross omega 0 over k b t, and therefore, C V, which is d E dt at constant volume, is going to be equal to 3n h cross omega 0 times h cross omega 0 over k b t square e raised to minus h cross omega 0 over k b t. So, this is nothing but 3n h cross omega 0 square over k b t square e raised to minus h cross omega 0 over kBT. As t tends to 0, this exponential factor goes down to 0 very fast, much faster than any polynomial, and therefore, this 1 over T square in front does not really matter, and the heat capacity C V will tend to 0 as T tends to 0. If I plot it therefore, T versus C V, I am going to get a curve. This fellow goes to 0 exponentially, and as T goes to large value, it goes to 3 R, roughly 24 joules per Kelvin per mole, and it goes to 0. So, this was the first calculation that was done by Einstein to show that quantum mechanically, if I treat the vibrations of a crystal quantum mechanically, that means the energy excitation is going to be with h cross omega, the C V indeed goes to 0 as T goes to 0. And this was a very, very nice discovery by him, and proposed that these vibrations should be treated quantum mechanically. Although the actual experimental test, it was found that the behavior is not quite as fast going to 0 as proposed by Einstein, it goes more as T cubed. So, we have to explain that, and that comes through Debye model. So, next we are going to discuss now is Debye model. So, remember in Debye model what we have is omega k is equal to velocity of sound times k. Density of states I am going to calculate now, again it does not hurt if I just repeat myself, is d omega, which is calculated through counting the number of states in k space. So, let me just do it quickly. In k space, the total volume of sphere that contains all the modes, and these are going to be acoustic modes, let us say is k d. Then the sphere of radius k d has volume 4 pi by 3 k d cubed, and the total number of modes is therefore going to be V over 8 pi cubed times this volume, and this is equal to the total number of modes. Let us do some cancellations. This gives me 2 pi square, and therefore, k d comes out to be 6 pi square n over V raised to 1/3. That is for one of the modes. And correspondingly, I would also have omega maximum, which I will call omega Debye. That is what this D stands for, which will be equal to V s k d, up to which all the modes will be exhausted. If you look at it slightly differently, what I am going to have is integral d omega integrated over from 0 to omega d should be equal to total number of modes, which will again give me, and I leave this calculation to you, is going to give me that omega Debye is going to be V s times 6 pi square n over V raised to 1/3. So, let us just estimate this omega d corresponds to what temperature, which I will call Debye temperature. So, Debye temperature, let me call it theta Debye, which is going to be equal to h cross omega d over k b. Omega d is equal to V s times 6 pi square n over V raised to 1/3. N over V is the density of atoms. So, if I substitute the numbers, V s is of the order of 1000. So, this is of the order of 1000. 6 pi square times n over V, n is Avogadro number, but I want to write in the units per meter cubed. So, it is going to be 6 times 10 raised to 29 raised to 1/3 roughly equal to 1000 times pi square is roughly 10. So, 10 times 10 raised to 29 gives me 10 raised to 30. So, that is going to be 10 raised to 10 and 6 times 6 is 36. So, I can write it as 36. 1/3 of 36 is roughly 3. So, this is equal to 3 times 10 raised to 13 radians per second, and therefore, theta d pi will be equal to h cross, which is 10 raised to minus 34 times 3 times 10 raised to 13 divided by k b, which is 10 raised to minus 23. So, this comes out to be roughly 300 k. So, let me collect all this and tell you that in Debye model, I have omega d, which is the omega max up to which all the modes are exhausted. That means, by this frequency all the modes are exhausted. So, this is the uppermost frequency that I excite, that is omega d. Correspondingly, there is a Debye wave vector, right, and there is a temperature theta d. Omega d is of the order of 10 raised to 13, k d would be correspondingly whatever you calculate this, I will maybe give it as an assignment, and theta d is of the order of 300 k. So, let us say 300 to 500 k. Let us calculate the total energy. Therefore, the total energy of the system is going to be integral 0 to omega d by v over 2 pi square omega square over v s cube, that is the density of states, times h cross omega over e raised to h cross omega over k b t minus 1 d omega. So, which I can collect different terms and write as v h cross over 2 pi square v s cubed integral 0 to omega d omega cubed d omega over e raised to h cross omega over k b t minus 1. That is the expression. So, the total energy is v h cross over 2 pi square v s cubed integral 0 to omega d omega cubed over e raised to h cross omega over k b t minus 1 d omega. To facilitate the integral, I am going to change variables to x equals h cross omega over k b t. So, that I have omega equals k b t over h cross x, d omega equals k b t over h cross d x for a given temperature, and the upper limit of the integral is x d, which is theta d by over t, and therefore, the total energy can be written as E equals v h cross over 2 pi square v s cubed 0 to theta d by over t. Omega cubed is going to be k b cubed t cubed over h cross cubed times d omega, which is going to be k b t over h cross dx. There is going to be an x cubed here and 1 over e raised to x minus 1. Collecting different terms, I am going to get from here E equals v h cross over 2 pi square v s cubed k b raised to 4 t raised to 4 over h cross raised to 4 integral 0 to theta d by divided by t x cubed over e raised to x minus 1 dx, which is equal to v kb raised to 4 t raised to 4 divided by 2 pi square Vs cube h cross cubed 0 to theta d over t x cubed over e raised to x minus 1 dx. That is the total energy in this volume V. Notice that there is a term here proportional to t raised to 4. If this theta d by t was not there, this is reminiscent of Stefan's law for phonons, where the energy comes out to be proportional to t raised to 4. There the uppermost limit, because the number of modes is infinity, so the proportionality is exactly t raised to 4. Here there is slightly more complication, but in appropriate limits you will see that limits the law becomes exactly like Stefan's law. So, if I take the limit of t becoming very small, in that case E becomes V k b raised to 4 over 2 pi square V s cube h cube 0 to infinity, and there is a t raised to 4 x cubed over e raised to x minus 1 dx, and then the dependence on temperature for the total energy becomes exactly t raised to 4, which is like the photon energy. And notice that this integral is a number, it does not depend on t anymore. So, this is exactly like photon dependence. On the other hand, if the temperature becomes very large, then the upper limit becomes very small. So, in the limit of t going to 0, I have E, which is V over 2 pi square V s cube h cross cube k b raised to 4 t raised to 4 integral 0 to infinity x cubed e raised to x minus 1 dx. This number is well known. The value of the integral is pi raised to 4 over 15, but anyway this is a constant. So, if I take C v, which is d E by d t at constant volume, is going to be come out to be 4 V k b raised to 4 t cubed over 2 pi square V s cubed h cross cubed integral 0 to infinity x cubed over e raised to x minus 1 dx. So, it is proportional to t cubed. How small this temperature? We are talking about temperature which is much less than theta d by. So, we are really talking about temperature T, which is much less than say 100 to 500, okay, depending on the material. So, we are really talking about temperature in the range of maybe 1 degree, 2 degree, 10 degrees or so on. In that case, the specific heat is going as T cubed. Now, let us look at the other limit. If I take T becoming very large, in that case I have E equals V over 2 pi square V s cubed h cross cubed k b raised to 4 t raised to 4 integral is 0 to very small number theta d over t x cubed over e raised to x minus 1 dx, and now theta d over t is a very small number. In fact, much less than 1, and therefore, I can write the integrand x cubed over e raised to x minus 1 as roughly equal to x square by expanding e raised to x minus 1 as x, and we get therefore E equals V over 2 pi square V s cubed k b raised to 4 t raised to 4 times theta d cubed over 3 t cubed. Now I can cancel certain terms. This T cubed goes with this T raised to 4, this becomes T, and I get energy proportional to T, and this implies CV is equal to a constant. Now notice that all this I have done taking only one mode into account. Now I should be actually writing E taking all three modes of 3-dimensional feature or 3n degrees of freedom into account as 3v over 2 pi square Vs cubed h cross cubed kb raised to 4 t raised to 4 0 to theta d by over t x cubed over e raised to x minus 1 dx. So, I have to multiply by this factor 3. So, as t goes to infinity, this e goes to 3v over 2 pi square Vs cubed kb raised to 4 t raised to 4 over h cross cubed 0 to very small number x cubed over e raised to x minus 1 dx, and e raised to x minus 1, the integrand now is only for small values, can be approximated as 1 plus x minus 1, which is equal to x. This is because I have the theta d over t to be much less than 1. And this immediately tells me that the integrand now is nothing but this integral is 0 to theta d over t x square dx, and therefore, I can write the total energy E as 3v over 2 pi square Vs cubed kb raised to 4 t raised to 4 over h cross cubed the times theta d cubed over t cubed. Cancelling this t cubed with t raised to 4 and getting t here, I get E is proportional to T. So, energy in the limit of large temperature comes out to be proportional to T. Let us see exactly what the expression is. So, I get E equals 3v over 2 pi square Vs cubed h cross cubed times kb raised to 4 t theta d cubed over 3. Again cancelling this 3, we get total energy equals V kb raised to 4 theta d by cubed over 2 pi square Vs cubed h cross cubed times T, and therefore, Cv, which is dE dt at constant volume, is going to be V kb raised to 4 theta d by cubed over 2 pi square Vs cubed h cross cubed. I leave it as an exercise for you to show that by substituting theta d by and all those things together, this actually is 3 n kb, and therefore, per mole it comes out to be 3 R per mole. So, let me summarize this lecture by pointing out that we have calculated total heat energy, if you like, so which I mean because of the temperature in a crystal by doing this integral 0 to infinity d omega h cross omega over e raised to h cross omega over kbt minus 1 d omega, and in the limit of large and small temperatures, we have calculated this in Einstein model. Where the heat capacity goes to 0 as t goes to 0, but exponentially, and we have calculated this in Debye model, where we had an approximation for omega k. So, here omega is a constant, here omega k depends on the material, on k as omega k equals V s k, and we have found that C v as a function of temperature goes as exponentially down in Einstein model, and as t cubed in the large limit both goes to 3r as t cubed in Debye model, and this matches with experiments. As a supplement to this lecture, I will send you some experimental figures that will show you the real graphs for real systems, where you will see this t cube behavior. Thank you.